So this worksheet is going to be going over bonding, Lewis structures, and formal charges, mostly stuff that was covered in general chemistry, so it's mostly going to be a review. First of all, what is a covalent bond? What is the definition of a covalent bond? This is, there's a lot of different ways that we would define this, but this is going to be 2 electrons or 4 electrons or 6 electrons that are being shared between 2 atoms. And this sharing of the electrons is what holds those atoms together, and what causes the atoms to come together to make a molecule. What are valence electrons? These are electrons that are in the highest energy level. Capital E is our abbreviation for energy, lowercase e with the subscript negative, that's our abbreviation for electron. So valence electrons are electrons that are in the highest energy level of an atom. They are also, a lot of times we define them as the electrons, I was going to say electrons on the outer surface, but a lot of times the terminology is the outermost electrons in an atom. So if we think about our model of the atom, we have a nucleus, and then we have some electrons that are, occupying this particular region of space that we might call n equals 1. And then we have more electrons that are occupying a larger area of space that we would call n equals 2, and so on. The valence electrons are the electrons that are on the outermost surface, or the furthest away from the nucleus, also corresponding to the electrons that are in the highest energy level. And the valence electrons are the ones that are used to make covalent bonds. That's not all that they do, but covalent bonds come from valence electrons. How many valence electrons are in these different atoms, carbon, hydrogen, and oxygen? So this is information we can get from the periodic table, which is why I have it opened up. If you remember from Gen Chem, one of the tricks that we have for counting valence electrons is to just look at the column that the atom is in. So everything that's in the first column has 1 valence electron, which means hydrogen has 1 valence electron. Everything that's in the second column has 2 valence electrons, which doesn't apply to question number 3. And then if we scroll over, everything in the third column has 3, everything in the fourth column has 4. There's our carbon. The fifth column has 5, and sixth column has 6. And hopefully you kind of remember this pattern from Gen Chem. And the only way that we really deviate from the pattern is that helium has 2, where all the rest of them in this column, they have 8. But those atoms never pop up in organic chemistry anyway, so it doesn't even really matter. So we will learn, or if we're being asked how many valence electrons there are, we will really literally get that information by looking at each one of these elements' location on the periodic table. And we'll use the valence electrons to help us draw Lewis structures, for example, the Lewis structure of methanol. Now, this is a molecule that might look more complicated than some of the stuff that we did in general chemistry, but it's actually not. All the molecules that we'll be drawing Lewis structures for in organic chemistry are easier than anything you did in Gen Chem. One of the cool things that we do in OChem is to write the formula of the molecule in a way that helps us imagine and visualize what the Lewis structure is. So writing the molecule in this particular, or writing the formula in this particular way, CH3OH, this is telling us that the molecule, we want to start by drawing a carbon atom, and the carbon atom should have 3 hydrogens attached to it. So there's 1, 2, 3. And then next up, we're going to have an oxygen atom. And after that, we're going to have a hydrogen. So we use that molecular formula to help us show the connectivity of the molecule. The oxygen atom does have 2 lone pairs on it. If you're using like your traditional general chemistry method of count up all the valence electrons, put everything together with single bonds, etc., you would come to this same structure. It would just take you a little bit longer. Another method that we use, like kind of as we're bridging the gap from Gen Chem to OChem, another thing that we can do is draw Lewis dot symbols for all of the elements. So for example, carbon would look like this, and then our hydrogens around it, which would look like this, and use those Lewis dot symbols to help us sort of visualize how the molecule would come together. And in this period of time where you're, transitioning your brain from Gen Chem to OChem and also recovering from summer break, it's going to take you a little bit of time to get quick at drawing Lewis structures, but it will happen. Next, we're going to calculate the formal charges for all of the atoms in this molecule, which is methanol. If any of them are not zero, we're going to write them onto the Lewis structure, and we'll use this space here to calculate the formal charges, and we'll do that with this equation right here. This isn't the only equation that's used to calculate formal charges, so if you're looking at a different resource that has a slightly different equation, don't panic. There's more than one way to describe how we calculate formal charge. Let's start by calculating the formal charge of this hydrogen atom right here. So this hydrogen atom, to do that, we'll go with the number of valence electrons for hydrogen. We decided that the number of valence electrons was 1, and then from that we're going to subtract the number of bonds. So we're looking at this hydrogen right here, and it has 1 bond, and then we're also going to subtract the number of electrons in lone pairs on this hydrogen. It does not have any, so that's going to be a 0. And that's for this hydrogen right here. Now, if we look at the other hydrogen, that hydrogen also has 1 single bond with no lone pairs, which means that its formal charge would be calculated the exact same way. A valence of 1, 1 bond, no electrons in lone pairs, formal charge of 0. And in fact, all hydrogen atoms that have just a single bond and no lone pair, they will all have the exact same formal charge. So we only need to calculate it once, and then notice that all of the other hydrogen atoms have the exact same number of bonds and the exact same number of lone pairs, which means that they're all going to end up with the exact same formal charge. So that kind of saves us a little bit of time. For carbon, let's do carbon next, right here. Carbon has 4 valence electrons. From that, we want to subtract the number of bonds around the carbon atom. So looking at the carbon atom, there's 1, 2, 3, 4 bonds. And we also want to subtract around the carbon atom the number of electrons that are in lone pairs. This carbon atom has 0 lone pairs, so that's a formal charge of 0. And then last but not least, we have our oxygen atom. We want to start with the number of valence electrons in an oxygen, which is 6. We want to look at this oxygen, count the number of bonds. It has 2. And then we also want to count the number of electrons that are in lone pairs. 1, 2, 3, 4. So all of these atoms have a formal charge of 0, which is the best possible scenario for any atom. So I'm going to put little smiley faces on there. Analyzing these formal charges, they all have a formal charge of 0, which is the most stable possible configuration. Formal charge equal to 0, that is the best thing that can happen to an atom. So we're going to use this to predict the stability of methanol. This is the part where we're kind of like bridging the gap between Gen Chem and OChem. How can we use formal charges to predict the stability? The formal charges in methanol are all 0, which means all of the atoms in the methanol molecule are living their best lives, and they don't want that to change at all. The molecule is perfect. So when it has all these formal charges of 0, that means that the molecule is very stable, which is another way of saying that it is non-reactive. It doesn't want to do anything. It's happy the way that it is. And if we do some sort of reaction with these atoms, chances are good we're going to disrupt this formal charge of 0 situation. We're going to give an atom a formal charge. We're going to change something that might not result in this continued streak of 0 formal charges. So this molecule doesn't really want to do much of anything, and that means that it's stable, that means that it's not reactive, that means that it's happy, it's in low energy conformation, everything is good about it. So now we're going to draw the Lewis structure of a methoxide ion, which is pretty similar to methanol. Methanol was CH3OH. This is CH3O with a negative charge. So I'm going to start with my carbon. The formula CH3 tells us that I have 3 hydrogens on that carbon, and then that's bonded to an oxygen atom, and that's it. There are no other atoms in the molecule. The oxygen atom has 3 lone pairs of electrons on it because it doesn't have a bond, and in order to give this oxygen atom an octet, for it to have 8 electrons around it, 2, 4, 6, 8 electrons. There we go. Calculate the formal charges of the atoms in methoxide, starting with our hydrogen. Hydrogen has one valence electron. Each one of these hydrogen atoms have one bond, and they have no non-bonding electrons. So the hydrogen atoms are still all perfect. The carbon atom, carbon has 4 valence electrons. The carbon in this molecule has 4 bonds, and it has no non-bonding electrons. So it also still has a formal charge of 0. The oxygen atom has 6 valence electrons. This oxygen atom has 1 bond, and this oxygen atom has 1, 2, 3, 4, 5, 6 electrons that are in lone pairs, which gives it a formal charge of -1. Because we have a formal charge, we want to communicate this by writing it on the Lewis structure. We're going to do that by writing this -1 formal charge somewhere in the vicinity of the oxygen atom. There isn't a rule that tells us exactly where it needs to go, like we don't have to write it in the upper right-hand corner or really anywhere in particular. We can just write it wherever we feel like it. I'm going to write it in the upper right-hand corner because that's kind of what we're used to in Gen Chem. And then one thing that we do with formal charges in organic chemistry that's a little different from Gen Chem, we draw a circle around them. That's just to help draw our eyes to those formal charges so that they don't get kind of lost in the structure. So we put the formal charge and we circle it. If it was a formal charge of a -2, we would still do the same thing and put a circle around it. If it was a positive formal charge, same thing, we'd just write the charge and circle it. Okay, so what do we think is more reactive, methanol or methoxide? When we're predicting reactivity, when anybody asks you to predict reactivity, we want to use our formal charges to help us make these predictions. Use formal charges to predict reactivity. So with methanol, the molecule on the previous page, all the formal charges were 0, which meant that it was completely stable, like perfectly happy. But with methoxide, what we're looking at right here, we have an atom that has a negative formal charge. That negative formal charge means that the oxygen atom is not perfect. There's something, off or a little bit wrong about the way oxygen is being, bonded in this particular molecule. And that formal charge and that imperfection is what leads to instability. So the more reactive would be methoxide, and this is because it has a formal charge of -1, but the methanol molecule formal charge is 0. Whether your formal charge is negative or positive doesn't make a difference. The magnitude is all that matters. If you have a formal charge of anything other than 0, that means that the molecule has reactivity and instability. And the more dramatic, more significant the formal charge is, the more reactive the molecule is. So if we also brought into the mix something that had a formal charge of -2, that would be even more reactive than a formal charge of -1. And then likewise, if we drew a molecule that had a formal charge of +2, that would also be even more reactive than -1, because again, all we're looking at is the magnitude. We don't really care about whether it's positive or negative. So last but not least, we're also going to predict which atom in methoxide is the most reactive. And this is what becomes really fundamentally important for us in organic chemistry. So when we're looking at this molecule, we've decided that the molecule is reactive, but what we really want to know is where is its reactivity? When this molecule decides to go out in the world and do chemical reactions, what is it going to be attacking with? What part of the molecule is going to be, running into other molecules and wreaking havoc? And still, same thing, we're going to use the formal charge to help us predict that. The hydrogen atoms and the carbon atoms all have a formal charge of 0, which means that they are stable. They are not reactive. The oxygen atom with its negative charge is the part that is actually the reactive part. So the oxygen is the most reactive, meaning that it is the most unstable because it's the one that has the formal charge.